Last little thing. So let's think about the energy involved in moving both translationally and rotationally. So let's bring that together. Up top, let's say this is like this cylinder. Sure, it's a cylinder, and I'm going to let it go and let it roll down to the bottom of the hill. At the top here, let's see what I have. I have potential energy, so that hasn't changed. But as I'm going, what am I gaining? I'm gaining kinetic energy because I can see that that center is going to go dunk, 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 all the way down to the bottom, right? So it is translating, it is moving along that path, but it is also rotating. The one thing we can't do is ignore the fact that it takes energy to rotate something. That's the merry-go-round thing. We just figured out how much energy is involved in the merry-go-round spinning. Now, and we already know that something has energy when it's translating, that 1/2 mv squared. So let's define that. 1/2 mv squared. And we define this as 1/2 I omega squared. So what this says is instead of straight, if I just go from this point to that point of going mgh to 1/2 mv squared, that now I also need to take into consideration the fact that I'm rotating. So I have this 1/2 I omega squared I. Now some fun things happen, and let me take care of the cranky dog. Now let's think of this. I don't know, what did I say it was going to be? Let's just make it a disk. So remember that disk, for disk, that I have inertia is 1/2 mr squared. Cool. I can make some substitutions here. Let's see, omega squared. Let's see, what does that equal with respect to velocity? And let's take the square out. What does that equal with respect to velocity? What do we say? So let's do it the other way around, because I think sometimes that's easier. That if I have something rotating, right? And I know that, like, if I'm sitting on out here and this thing is rotating like that away. Didn't we say that, so here is the rotation and I have some sort of tangential velocity. So this tangential velocity is going to relate to omega, because remember the whole disk rotates at the same rate, with respect to how far away it is from the center. So if I am rotating, then my tangential velocity is going to be that rotation times the distance away that it is. That means that omega is going to be velocity divided by r. And why do I bring that up? Because I feel like we can simplify this down. Go ahead, let me go with pink. Pink's good. It's been ignored for a while. So I have mgh equals 1/2 mv squared plus, this is the reminder not to lose your fractions here, 1/2, here's my I, which is another 1/2 mr squared. Now my omega is squared, and my omega is velocity over r. So v squared over r squared. Oh, didn't I say things were going to cancel? Look at that. Look at this. So let's rewrite it. mgh equals 1/2 mv squared plus 1/4 m, oh, r's cancel, v squared, mv squared. Oh, masses cancel. This is nice. Now, what do I have? I have 1/4 plus 1/2, otherwise known as GH, otherwise known as, let's see, 2/4 plus 1/4, otherwise known as 3/4. v squared. So the velocity I end up with at the bottom is now going to be like 4/3, and then the whole square root of that. So I can solve this again. Let's just move this so you can see it. 4/3 GH, take the square root. So another way to look at that is 1 1/3, right? And when we were just going from height to kinetic, so potential energy to kinetic, we had something that looked like this. We had mgh equals 1/2 mv squared. So masses canceled again, and I end up with 2gh is my final velocity. So what you're seeing here, this difference between this 2 and this 1/3, or this 4/3 rather, is the fact that it takes energy to go into that rotation. So I can't get to the same amount of velocity when I'm rotating, just letting potential energy get me to the bottom. If something is just sliding down, so a box sliding down is going to have a higher velocity than, say, this disc that's rolling down. And we can do that same kind of comparison. So this, let's be clear here. This is just kinetic and potential from translation. This is from, let's make that equal to V. This is from rotation. So something rotating, going down a hill. Rotating. The other thing you can do then, and I'll leave this to you to do, is you can look at the example, the handout 10-18. And I have, what do we have? We have an empty can, we have a solid cylinder, I have a sphere and a hoop, and they're all sliding down. And I want to know who gets down to the bottom first. You will notice that you can make this substitution when we're doing these energy things and make life really pretty at the end, where you're not dealing with a bunch of values spread out, you know, like this ugly thing here becomes this nice kind of condensed thing. Be really careful with your fractions. Don't lose the fraction that goes with your, hi Rika, with your inertia. Okay, be real careful with that. Again, go to your book, and on the handout, actually, I gave you the fractional definitions for all of the inertias for the ball and the ring and the hoop. And so you can look that up, and then you can give it a go. Let's see, what do you think is going to happen? What does it mean? What does it mean for something to have a bigger inertia? If I have a large inertia, do you think that means it's going to take more energy to rotate it or less energy to rotate it? Remember how we defined inertia. So first ask yourself if you can kind of get an intuition just by looking at the inertias. And then I really suggest that you do some practice with this so you can get pretty fast with that. So when you come to the final, it's not overwhelming. This is something that's pretty easy for you to do. All right. With that, that's the last video of the quarter. And good luck on finals. Don't forget to let me know if you have any questions.